Okay, so I decided to kind of make this problem up for us, and let's say that we're going to do an apportionment. They're going to have like a committee of parents for all of North Point, and they want the number of parents in this committee to represent the number of children in these different kind of levels or programs. So I totally made these numbers up. I have no idea how many students we actually have in different things. I just figured for elementary, like 20 students per level, and how many levels are there? Of those, there aren't all the years of Spanish immersion yet, because I think we only go up to 3rd grade right now, and they increase a year as those kids move up. But it only goes up to 3rd grade right now. So I just kind of made those up. I figured middle school, let's say they have 60 students per grade. I have no idea. I think they probably have a little bit less than that, but we'll just go with that. And then for high school, I said let's say we have 90 students per grade on average. So I just kind of made these numbers up, but I think they're, reasonable-ish. So let's say there's this many students in each of the programs, and let's say we're going to have 40 parents on the committee. So we're going to have 40 seats on the committee. We're going to do the apportionment all 4 ways we learned. Okay, so we're going to start with Hamilton's method, and then that's one we learned all the way back on Monday, and then we'll do the 3 that we learned yesterday, Jefferson's, Adams, and Webster's. So, for Hamilton's method, we need the standard divisor. The standard divisor is the total population. So we need to add up how many kids are in all of North Point, according to my numbers, is 860. Divide by how many seats we're giving on this committee. $21.5. So what that means then is on average for the entire whole population, each representative should represent approximately 21.5 people. But it's going to be different per each level a little bit. So then what we need to do is find the quotas for each of them. So to find the quotas, we take their population and divide by that standard divisor. So 180 divided by 21.5 is 8.372. 140 divided by 21.5 is 6.512. 180 we already did, again 8.372. And 360 divided by 21.5 is 16.744. So those are their standard quotas. Then, for Hamilton's method, we round everybody down. So 8, 6, 8, 16. And we see how many we've given out. Which is 38. That means we have a surplus of 2. So we're going to give 1 more to the 2 people with the highest decimal places. So 0.7, the high school is going to get 1 more. And 0.5, the Spanish immersion is going to get 1 more. So then our final apportionment would be elementary English gets 8, Spanish immersion 7, middle school gets 8, and high school gets 17. And that would be our 40 seats. That's Hamilton's. Questions on Hamilton's? So then next, we're going to do Jefferson's. For Jefferson's method, we want to use a modified divisor. And our modified divisor is always going to be smaller than the original divisor. So if our original divisor was 21, let's say we're going to try, or 21.5, let's say we just try 21. Okay, for Jeffersons, you always want to go smaller. So we're going to try a divisor of 21 and see what our new quotas are. We don't care about the decimals here because we're not going to give out any surplus because the goal is that we don't actually have surplus. So we're going to divide the populations again. So 180 divided by this new divisor of 21. I get 8.57, but all I care about is the 8. We don't care about the decimals at all. Then I'm going to do 140 divided by 21. And I get 6 2/3, but we're just going to do 6.
So you round down for Jefferson's too?
Yep.
Okay.
Yep, you go smaller and then you round down. 180 divided again is going to give another 8 because it's the same as the other one. And then 360 will give 16, I think. I made that up, I don't know. 17. I shouldn't make things up. 17. That's one too few. If I add that up, I can tell that's one too few because I look at what I had last time and they're all the same except for this one, which is one smaller, right? So that's not right because we have a surplus and we're not supposed to have a surplus. So trial and error, let's try 21.25.
What did the total end up being?
39.
Oh.
And it needs to be 40. So we'll try 21.25. Wait. If it's too small, choose a smaller. So we'll, yeah. So 21.25. No, choose a smaller. No, on erasing. Okay.
Maybe like 20.75 or something.
Yep. So if it's too small, choose a smaller. It was too small because it was only 39. So now we're going to try 20.75. So 180 divided by 20.75 is 8.67, but that's just going to be 8. 140 divided by 20.75 is 6.7. It's going to be a 6. We're going to get another 8. And 360 divided by 20.75 is 17. And it's exactly the same as it was last time. So I guess we need to make a bigger change. So let's maybe go all the way down to 20. We go all the way down to 20. 180 divided by 20 is 9. Oh, that's probably going to be too much now. 140 divided by 20 is 7. Yeah, it's going to be too much. Too much of a change. $20.25. Don't you love guess and check? This is dripping with sarcasm because I hate it. So 20 point.
You're gonna like have nice
25.
numbers on the test, right?
Well, I mean it's guess and check, so
Yeah,
it's.
What
I
if you
mean,
like 997?
so it'll be nicer than that, yeah.
Okay, that's all I need.
So this is 8.888. It's gonna be 8. Is 6.9. I think this is not gonna be right. And 360 divided by 2.25.
You know, tests right before the end of a marking period are really overrated.
You know, the end of the marking period is also the end of the class, so we have to have it before the end of the marking period because we can't have it at the beginning of the next marking period because we don't have a beginning of the next marking period. So it's not that it's not a bad thing, it's just that it's the only thing. That was too small, so we need to go smaller, 20.1.
We could go through all the infinity.
Wait, how is 20.1 smaller than 20?
It was smaller than 20.25. Was the last one I tried, was 20.25. 180 divided by 20.1 gives 8.9. Divided by 20.1 Oh, 6.96. Okay, so this is gonna be too small again.
Yeah.
We don't have to go to that.
Open note completion grade.
Oh, 5. Well, having your notes isn't gonna help you be a better guesser.
Right.
That's the thing. Like, this just stinks, and there's no way around it. Like, it is a thing. There's nothing to do to help with this. It's 8.97. 140 divided by 20.05. 6.98. Are you kidding me? How do I get this thing to be 7? It should have worked for 20. We did 20, right?
Yeah.
2.00.
Oh, it's 20. I don't know why this. Did anybody find one that works? Because sometimes you guys work faster than me.
No. I have tried.
Oh, 3?
0.02.
180 divided by 20.03. And 140 divided by 20.03. It's got to be 20 or smaller. How did that happen? Why isn't it? I don't know. I don't know why we can't get it to work. But you did the process, right? I promise all the ones on the test will work.
Something I
Yeah.
don't quite understand is that 21.1 that proved to be too small, right? Because we only got 39, right? We need 40.
Right.
So how come we've been doing why haven't we been doing 22?
When it's too small, you go smaller.
Oh. I'll try to make sense of that.
Yeah. So when it's too small, you go smaller. So I don't know. That's frustrating, but here we go. We'll just say we don't know. I'm done trying on that one. The next one that we did was Adams. For Adams method, you want to choose a divisor that's bigger, and I have a feeling if Jefferson's didn't work, Adams didn't work, because they're pretty much partner process problems. But you always round everything up, and you choose the bigger divisor. So I'm going to say, let's just, to give it a shot, try 21.6. Okay, just to give it a shot. So we want to go bigger than the standard. So 180 divided by 21.6 is 8.33, but I am still going to call that 9. Even though it's only a 0.3, you round everything up for Adams. Which is why I feel like it's going to give us too much.
So what number? It was
Yeah.
8.33.
Yeah, 8.33, and I'm rounding that up to 9. 140 divided by 21.6 is 6.48, but I'm going to go up to 7 on that. And then 360 divided by 21.6, 17. And there's too many seats that we gave out, so we would need to adjust. If it's too big, go bigger. So then we should try 21.7 or 21.8 or something like that. We'd want to choose a bigger divisor. If you're giving out too much, too big, go bigger. Too small, go smaller. Okay, so that at least makes it easy to remember. You go the same way. But if one of those is causing us problems, the other one is too, because I'm wondering, did I is the standard divisor right? Did I make a mistake on that? No, it's just bad numbers. And then the last method is Webster's method. And Webster's method does the combination of the other two methods. So for Webster, what you do is you start by using just the standard divisor, and you round everything the way that normal rounding happens. So 0.5 goes up and below goes down. So if I do 180 divided by the standard divisor, 21.5, we get 8.37. I round that down to 8. 140 divided by 21.5 is 6.5. that rounds up to 7. And then for the last one, 360 divided by 21.5 is 16.7. So that rounds up to 17, and that worked. So it's just those other two. There must be like, you must have to adjust it by pretty much nothing, but still something. I don't know why. It's just, I'm bad at guess and check, and it's not a guessable thing here happening for me. So those are those. You also need to know Huntington Hill. So for Huntington Hill, the formula was the population squared, old representation, new representation.
So we need to know like the definition of a paradox.
You need to not necessarily know the definition of them, but like we did in that assignment, you need to state which paradox something
We have to
is.
say why.
Yes. So to find a Huntington Hill number, you want to take the population. So like, let's say we're doing the high school, 360, square it. Old representation, let's say was 17, and let's say new representation would be 18. And it only goes up by 1. You only ever want to give one more person at a time. So whatever your old is, and you should do one more for the new. So our Huntington Hill number here would be 360 squared, and then divide by 17 and 18 gives 423.529. Now let's say, what if we gave an extra one to the middle school? It said their population was 180, and they had 8, right? And so they would go up to 9. So 180 squared divided by 8 and 9. Their Huntington Hill number is 450. So according to those two numbers, if we're going to give out a new representative, who should we give it to? The high school is the first one, the middle school is the second one. We're going to give it to the second one. You want to give it to the bigger Huntington Hill number. Gets the next representative. So remember the homework, there was that chart with like, if they have one representative, these are their numbers. If they have 2 representatives, these are their numbers, with like the carpenters and the plumbers and stuff like that. Taking a good look at that homework problem would not be a bad idea. Yeah.
When we have the Huntington Hill problems on the test, will they be based off the numbers from the previous problem?
Yes. Basically the whole test uses the same setup, the same populations and stuff like that. So it's like all just different parts of one setting.
And you just use the normal standard divisor to get these numbers, right? From like the first Hamiltonian thing to get the 17.
Yeah, so you'd use their representations from the Hamiltonian. Yep. The way we did it in that chart is to find the initials. The way that you would give a Huntington Hill number to start with, so like in that chart, the whole chart was assigned, but if you needed to fill them in, we'd want to start by saying, what if they just had one representative? So what we would do is start by giving everybody one representative, because that's fair. Everybody needs to be represented. So like for the high school, we would say they have one representative to start with. What if we raise it to 2 representatives? And that would be their first value in that table. So that would be 128. Then the middle school, let's say they have one representative and we raise them up to 2. Wait, that 128 is not right.
No, it's a really big.
It's really, really big.
6480.
So then for the middle school, it's 16,200. The English elementary school was the same as the middle school, and then the English Spanish the Spanish immersion elementary school was 140. And so their number would be that. And so those would be the numbers in that first row of the table. That's how you'd find those first rows. Now, given those values, who should get the second representative? The high school, because they have the biggest number. So then what we do, if we have that chart, say we have this chart that says like elementary English, elementary SI, middle school, high school, and then off to the side it says if one representative, and these would be the numbers that would be in that row, okay? And we say, okay, the high school is the biggest. So now when we do the next step of the problem and we want to give out the next representative, we would be using these values and that one. Because now high school has two, because we just gave them another one. And the other ones still only have one. Okay, but everybody starts with one representative, because that's fair that everybody's represented. And then we start adding on representatives individually based on whoever has the highest Huntington Hill numbers. Okay, until we've given all of them out. Okay? Paradoxes, there were 3 paradoxes. There's the population paradox, which says if one population is growing faster than another one, they should earn more representation because they're growing faster. We had the Alabama paradox, which says, let's say we increase representation. So instead of having 40 parents, let's say we decide we want to have 41 parents. If in doing that, it causes somebody to lose a representative, that doesn't seem right. It should just be that somebody gets an extra one. It shouldn't be that somebody has to lose one. That's the Alabama, that somebody loses. And then we have our new states population that says, what if we developed a new program in our school? I suppose we could do like the homeschool hybrid program. We're like, oh, shoot, we should probably represent them too. So we bring them into this and then decide, to be fair, let's now have 45 on the board, but yet still one of the old programs would lose a representative. That shouldn't happen. Okay, so those are the 3 paradoxes that are possible to